Switch slides. Well, welcome everybody to tonight's talk as part of the Astronomical Society of Edinburgh's sort of lockdown series. You can find out much more about the Society on our website. You'll find links there to our Facebook page and our Twitter feed. And indeed, all the talks that we've had during the lockdown period are available on our YouTube channel. So if you go to the website, you'll be able to access all of those. Thanks, Mark. And just a note coming up on Friday, it is, I think, the final in our astro imaging introduction, part 5, and it's about imaging for science projects. So where amateurs can make a contribution to live science projects. So Mark will cover that. And on the 31st of July, we're going to sort of have a end of term roundup where we'll talk about what we've done during the lockdown period and what some of the shape of things that we want to do going forward. We're going to not have a meeting during August and have a break. Having said that, the Irrepressible Imaging Group will be getting together on the 12th, and that's for members only. The talks will recommence hopefully on the 4th of September. I know Carl is talking to a speaker about fast radio bursts, so hopefully we'll be doing that. And then the imaging groups on the 9th. Thank you, Mark. So tonight we have Dr. Nour Raouafi from the Parker Solar Probe team in Maryland. I understand he's the Chief Scientific Officer for the project. And as usual, questions. If you've any questions and you're on Zoom, put them in the chat box and Peter will call your name at the end. And if you're watching live on YouTube, then pop them in the comments section and we'll try and pick as many as we can in the time we have. So I'll hand over to Dr. Raouafi and I'll ask you to share your screen. Thank you very much.
Sure. Thank you so much, Andy, for the nice introduction and welcome everybody. I am, as Andy mentioned, I am the Parker Solar Probe project scientist. And let me ask you, do you see my PowerPoint?
Yes, we see your screen, but not in presentation mode.
What about now?
Correct.
Okay, great. So Parker Solar Probe launched almost 2 years ago. We will be celebrating the second birthday of the mission in just a few days. On August 12th, the mission will be 2 years in space. What are you seeing, the presentation mode or the?
No, we're seeing your presentation mode.
Okay, great, fantastic. So let me start with this, and I'm going to talk, give an overview on the mission and also on the some of the discoveries we made so far. We made a lot of discoveries, so I will not be able to cover everything in just one seminar. So I will try to give you an overview and highlight the most important discoveries we made so far. Let me start with this. This is the a series of images from Parker Solar Probe of the Neowise comet. And I went the other day outside to see it one more time before it disappears for the next 7,000 years. And something, by the way, Parker Solar Probe is not really meant to study these objects, but we take advantage of any opportunity to do extra science from this fantastic mission. And anyway, while I was watching the comet, I was also looking at the sky, and it occurred to me that as a solar physicist, I focus most of my time on the sun, which is the star that is closest to us. But that night in particular, when I was looking up, it occurred to me that there are tons and tons of stars in the galaxy and the universe. And if you think of it, the universe contains billions of galaxies, and each of these galaxies contains billions of stars. And there are many, many of them. They have planetary system orbiting them. And there is the potential of extraterrestrial life out there. And we are obviously looking for it all the time. Now, going back close by, so the question that I had, what kind of insight we have from studying the sun into all these billions of stars we are observing each night? So we are so lucky to have a star like the sun close by, where it has a habitable zone around it that is us, Earth, and we can study it in details. And whatever knowledge we gain about the sun, we can project it into other stellar systems that are not accessible to us because of the distance. One example in particular, it is the outer layer of the sun, which is the solar corona that we can see during a solar eclipse. And this layer here, it is so mysterious. There are certain manifestations that happen there, and they are mysteries for decades now. We discovered them. One of them is over 8 decades ago, but we are still struggling to understand what is the origin of that phenomena. And I will talk about some of this phenomena a little later. Anyway, and during this is the solar an image of the solar eclipse of 2017 that crossed the United States continental from coast to coast, the continental US from coast to coast, and you can see that the sun itself is very quiet during that period, but the corona is so complex. So the corona is always complex regardless whether the sun is quiet or it's active. And that complexity is actually at the base of this mysterious phenomena that I mentioned a little earlier. So what is the interest for us to study the sun, and in particular the solar corona? We basically live in the extended atmosphere of the sun, that is the extension of the corona that we call the solar wind. And whatever happens into the solar corona will affect us in many ways, sometimes adversely. And this example I'm showing here is one of them. This is the blackout of 1989, which is caused by a huge solar event. It's a CME that erupted in the sun that caused the power outage in the northeast US. Now, let me give you another example that is more recent. In 2012, there was the most powerful explosion on the sun. It's a CME that erupted in July 2012, and it missed Earth by a week. So had it happened a week earlier, it will hit Earth. And the estimate of if it hit Earth, the estimate of the losses are above $2 trillion. So this is actually why we need to understand the solar corona, because of this magnetic activity occurring there. It can affect us in our lives here on Earth and also in space. Now that, in particular, now that we're thinking to send humans to the moon and to Mars, and if we are going to send them there, we have to protect them. And the best way to protect them is try to predict these events, and we cannot predict them if we don't understand how the sun and the corona work. Now, let me go to these big 3 mysteries that particle solar probe will try to help us understand. The first one is what we call the coronal heating problem, and it was discovered, by the way, in the late 30s. And as I said earlier, we don't understand it to this day. We don't understand how the corona is much hotter than the solar surface. The temperature of the solar surface that we see with naked eye is at about 6,000 degrees. You move a short distance above, and the temperature of the plasma will jump to more than 1 million degrees. And that is kind of counterintuitive, because from everyday experience, if you move away from a heat source, it gets cooler. Obviously, that does not work for the solar corona. The second problem is, which is closely related to the first one, is what we call the acceleration of the solar wind You look at this plasma at the plasma at the base of the solar corona, and it is almost standing still. The velocity of the particles is between 5 to 10 kilometers per second, but they get accelerated to hundreds of kilometers per second over a very short distance. And there again, we don't really understand where they get the energy to get to these high speeds. The third one, which I talked about earlier already, is explosions on the sun in the form of flares and coronal mass ejections. And every time we have a powerful one, they will accelerate a certain population of particles to almost the speed of light. And these particles that we call solar energetic particles are extremely hazardous to space equipment, to space exploration, to human in space, and also to the ground here, as I showed in the example earlier of the blackout in the Northeast America. So Parker Solar Probe will look at these three phenomena, but let me say this. Parker Solar Probe is an exploration mission. We are stepping into a region of space that we never visited before. And whatever observation we are going to make there is a potential discovery. And that is exactly what we are learning from the data. We are learning a ton of new things that we didn't know before, although we have been studying the sun and its atmosphere for decades and maybe centuries now. But there are new things. Once you get to the source of this phenomena, you discover the new subtleties that escaped us for a long time. Now, a little history about the mission. Parker Solar, the idea of sending a probe to the sun is not new. It dates back to 1958. If you look at the report of the Simpson Committee, you see that the second mission, actually the first one, which is a solar probe that will orbit the sun within the orbit of Mercury. That is actually Parker Solar Probe that we are having now. And there are two other missions. That is one that orbits the poles of the sun, that is Ulysses, the European mission. And the third one, which is B here, it's another mission that will leave the solar system and basically venture into the interstellar medium. Parker Solar Probe has been named after a physicist named Eugene Parker, who published in 1958 a paper basically predicting the existence of the solar wind, the supersonic solar wind. Okay, since then, there were tons and tons of studies. NASA commissioned different institutions to try to implement this mission, but it's extremely challenging. It is only in 2008 when when a study came from applied physics lab at Johns Hopkins, basically came up with a concept that is affordable, but also it leads to a fantastic mission that can orbit the sun for a long time. Now, let me say a few words why it took us almost 60 years to get to this point. Obviously, when you orbit a star close by, that environment is extremely harsh. And if you don't protect your spacecraft, you can lose it in seconds. And therefore, you need structures like thermal shield here that I'm pointing to here that can protect your spacecraft from that environment. And that material have been only, we knew that material exists only recently. You also need new technology almost everywhere, like solar panels that are water cooled. That is a first in space. We never flew solar panels that are water cooled in space. This is the first time that is done. You also, for the solar panels, you cannot really fly conventional solar cells. You need a new generation that can survive the photonic flux from the sun when we are close by. And also you need, in terms of science, you need state-of-the-art instrumentation to make the most sensitive measurements around in space plasma. Obviously, after 60 years, Parker Solar Probe is reality now. It's been in space since August 2018, and they, as I mentioned earlier, the mission is doing really an amazing job. It is behaving way, way better than we expected. We are getting a ton of data out of it. We are actually bringing 4 times more data than we planned to bring down. And obviously, as I said, the number of discoveries that we are making is huge, and we are only at the start, and the team is small. So the expectation for this mission is that this data will be used by researchers for decades and decades. Now, as I said, we launched last year in August 12, 2018. We will orbit. We will fly by Venus 7 times, and every time we fly by Venus, we get closer and closer to the sun. But the ultimate goal is to get to 3.8 million miles from the solar surface, and that will happen in 2024. Let me say this, that's actually 2025 is the end of the nominal lifetime of the mission. But we have, if the spacecraft and the payload are healthy by then, we can extend the mission by many years. We have a lot of fuel in the spacecraft, and virtually the mission can go for decades after that. But there might be other limitations as well that will probably end the mission. But the goal is to probably reach the other solar minimum, because we launched in a solar minimum. By the end of the prime lifetime of the mission will be at solar maximum, and we hope to at least cover a full solar cycle. Sorry. Okay. Now. In terms of the payload in particular, most of the instruments reside behind this heat shield here, and the most of them they reside in this structure, which is hexagonal structure. We call it the bus, and all of them operate at room temperature. When we are at the closest approach of the sun, the face of the heat shield that is on the side of the sun will be glowing at more than 2,500 degrees Fahrenheit, which is about 1,500 degrees Celsius. The other side, which is only 4.5 inch, will be at about 700 degrees Fahrenheit. And 1 meter behind, it will be at room temperature. The only exceptions for the payload to this is the electric antenna of fields, and also the Faraday cup from another instrument suite, which is SWEEP, that I will talk about in a moment. These are the only exceptions. These instruments are exposed to the full solar environment. The rest of the spacecraft is operating in the shade of the heat shield. So in terms of payload, we have 4 suites. We have WHISPER, which is the only imager in the spacecraft, and it observes on the side of the sun. It observes basically the solar wind as it gets convected from the base of the corona all the way past Earth. The fields, which has the electric antennas, but also have magnetometers on the boom, will measure electric fields, magnetic fields, densities, temperatures, and all type of fluctuations in the plasma waves and all that. ESIS is the I'm looking for my the cursor here. ESIS is the energetic particle suite. It measures energetic particles that come from flares and CMEs, and SWEEP, which has 3 sensors, measure the thermal solar wind. Now, I mentioned this earlier. We actually launched at solar minimum. By the end of the prime mission, we'll be at solar maximum, but the hope is that we extend the mission all the way down to the other minimum, and hopefully even be beyond that. Now, so far we covered 5 orbits out of 24. This is actually the highlighted here is the 5th orbit. As I mentioned earlier, we are doing way more than we predicted. Pre-launch, the main science phase for each orbit is what we call the encounter, is when the spacecraft is within a quarter of an AU from the sun. It is the yellow portion of the orbit here. But after launch, we discovered that the spacecraft is way better than we designed it, where we intended it for. So now basically the instruments are on almost all the time, except when we are downlinking data, we have to turn them off. But apart from that, they can observe around the orbit. Yes, this is another view graph that shows where we are. We did the first Venus flyby, second Venus flyby, and 10 days ago, we did the third Venus flyby, which is this one here. And after that, the perihelion will drop from 27 solar radii to 20 solar radii, which is a big jump. And after this third Venus flyby, we have 4 more, and that will get us to the last 3 orbits, which all are at the same perihelion of 9.86 solar radii from the sun center. Now I'm going to talk a little bit about the some discoveries of the mission, and I will cover discoveries from the 4 suites, instrument suites. I will start with WHISPER, which is the imager. This image here, it's from SOHO, which is the ESA NASA mission that launched in 1996. We from that mission and from others, when we observe the corona, we are used to structures like this, like what we call coronal streamers, and usually we see them. They are bright structures. They are more dense than the rest of the corona, and the magnetic field is a little stronger there as well. But we don't have really access to their fine structure. All we see is just a blob of bright material, and that's all we see from one AU. This is now the image, the first image that we released for the Parker Solar Probe mission. It's very similar to the streamer I showed earlier, except that now we see fine structure within coronal streamer as well. So the value of this image tells us whenever you get closer to the source of the of any phenomena, you get way more insight into it. Now, this image can be a little bit misleading. It shows us the fine structure, that is good, but look at it. One more thing. Let me go back to the slide before. These streamers in particular, usually we see them very quiescent, except every now and then there is something that comes out of them. What we call it, it's a CME. We call it the blowout streamers, but they occur every now and then. They are not frequent at all. Apart from that, these structures are very quiescent. Now, look at them when we get very close to them. And this is the movie from the first encounter of Parker Solar Probe. You see all these dynamics here. We miss all of that from Earth. We don't see it. But when we get closer there, we see a multitude of small CMEs that we call flux ropes that are erupting one after the other. And there are a ton of other fine structures, like outflows, like turbulent flows that we see in this portion here. Let the movie come back again, and we will look at it. On this portion here, you will see some turbulent flows there as well. And all these fine structures, we cannot see it from Earth. So getting close to this structure, we are discovering a new nature of them. This is another set of movies from another orbit, where we also see CMEs, and we see them in way more details than we've seen them before. Same thing here. There is a big CME that is erupting on this side here with a lot of outflows elsewhere as well. Similar thing. Yeah, it's playing now. This one is the best CME we got so far, and this one obtained during encounter 3. And it's, when you look at its internal structure, it's amazing. And we look at it from Earth, we see just a blob. But going there, you discover there is a multitude of magnetic structure within that big envelope there. Okay. Let me go to another thing that was also discovered by WHISPER. Going back in 1929, a researcher named Henry Russell predicted that there should be what is called a dust-free zone around the sun. When you look at the heliosphere, there is dust everywhere. Further away, it's big chunks of dust, but due to grinding, due to collisions, when you get closer and closer to the sun, the size of these dust particles gets smaller and smaller and smaller. And when you are close to the sun, you heat the smaller particles much better than the more efficiently than the big particles. At certain point, when you are very close to the sun, these particles get very hot to the point that they evaporate. Once they evaporate, they get cleaned up by the solar wind and the radiation pressure of the sun. And the end result is a dust-free zone. It's a zone where dust is depleted there. The issue with this prediction is, since for the last 90 years, people look at it over and over and over, but there was no evidence whatsoever for it. And the big question was, yeah, we see dust everywhere, but is there really a dust-free zone around the sun? We believe Parker Solar Probe is giving us the very first hint for the existence of this dust-free zone. Here, what we are looking at, it's a movie from the first orbit of the emission by dust in the solar corona. And if you plot the intensity of this emission along this axis here, this is what we get. So the dashed lines here and the two dots here are measurement of that intensity as seen from 1 AU. And you can see it that is increasing all the way to the sun. It doesn't decrease at all. And if it doesn't decrease, it means there is no dust-free zone. But when you look at these intensities as seen by Parker Solar Probe, you actually see a decline in that intensity as you get closer to the sun. And we expect this decline to be bigger as we get closer and closer to the sun. We believe this is the very first hint of the existence of a dust-free zone. And if this is confirmed, this is really a big and historical discovery of the mission. Now, we continued after the first orbit and second orbit looking at the same measurements, and we get more confirmation of this decline. Here in particular, we have models, we have the measurements, and they are very, very close to each other. And that's we believe now we are really at the edge of the dust-free zone. And as I said, this is a huge discovery, and it's another constraint on models that are dealing in particular with dust in the heliosphere and elsewhere, and dusty media in the universe, how dust evolve and behave around stars in particular. Now, let me remind you just very briefly that two of the objective of the mission is to explain the heating and the acceleration of the plasma in the solar corona. That is the coronal heating and the acceleration of the solar wind. In other words, what we are looking at solar energy sources that is available to the plasma to use in the form of heat and acceleration. And obviously, these sources escaped us for the last 60 years or more. Now, we knew that the Parker Solar Probe is going very close to a star, and it's flying through a magnetized medium. And the magnetic field there is very complex. How complex it is, we don't really know because we don't have the measurements. Let me go to the next slide, and I'll show you. From historical mission like Helios, like other mission around like MMS, like others, we are used to the magnetic field to fluctuate a little bit because you are flying in a plasma, and obviously there are waves, there are other disturbances. But the amplitude of these fluctuations is very small. This area here is the region that was not explored before Parker Solar Probe. Look at what Parker Solar Probe is observing. These fluctuations, when you get very close to the sun, are extreme. They bring the magnetic field from one polarity all the way to the other polarities. By the way, the two red dashed lines are the envelope of the where the magnitude of the magnetic field. We call these structures switchbacks, and basically what we are looking at kinks in the magnetic field. As Parker Solar Probe fly around the sun. The magnetic field will bend all the way back to the sun and comes back out again. And this structure, their time scales goes from a few tens of seconds to several minutes. But we are seeing them all the time as we get close to the sun. Now, okay, let me show this animation. It shows them much better here. Basically, they are structured like these ones. It's just a bend in the magnetic field. So one might ask, okay, what is the big deal about this? Why they are so important? First of all, from a phenomenological point of view, the magnetic field is like a rubber rope. Whenever you twist it, it will try always to untwist. So creating the structure in the magnetic field and maintaining them for a long time is very challenging. And that is actually testimony that there must be a source, energy source that is linked to the structures that creates them in the first plane, but also maintain them as they propagate all the way out into the solar wind. And that is actually confirmed when we look at the energy content of the magnetic field and also the plasma. Let me, this is the black line here is the magnetic field strength. This one is the density of the plasma. This period here, the magnetic field is very quiet. But here is when we hit a group of these switchbacks. By the way, we call them switchbacks. When we hit a group of them. During the quiet period, the energy content of the magnetic field and also the plasma is very low. What we are looking at here is the pointing flux into the kinetic energy of protons. But once we hit the region where we encounter the switchbacks, the magnetic field in the plasma becomes very, very energetic. That is actually testimony, it's a smoking gun that this new structure that we're discovering now, they are probably it's a potential source for the heating and the acceleration of the plasma. In particular, that we are seeing them all the time when we get closer to the sun. And another also hint of them, once we move out away from the sun, we see much smaller number of them, meaning that this structure dissipates as we move out, as we move away from the sun. In other words, the energy content of this structure is already dissipated into the solar wind, which causes the heating and the acceleration. And there are actually now, there are other papers that shows that there is excess heating within these switchbacks. So this discovery basically links back to the first two objectives of the mission that are what causes the coronal heating and what accelerated the solar wind. There are other features as well that are also potential candidates, which are waves. I will not talk about waves here because it's a huge and complex topic. But Parker Solar Probe is observing all sorts of waves, and these waves get sometimes unstable, and they also cause heating and acceleration as well. Now, let me move to SWEEP now, which is the instrument suite that measure the thermal solar wind. But before getting to the measurements themselves, let me say this. When you have a star, and by the way, this animation is not for a star, I believe it's for a planet, but I'm using it here just for the analogy. When you have a star and you have a magnetic around it without plasma, the magnetic field will rotate rigidly with the star. But if you load it with plasma, the behavior of the magnetic field will change. It will start bending backward. And the reason for that, when the magnetic field is strong enough and dominates the plasma, it will impose its will on the plasma. It will rotate with the star. But further out, it's the opposite that happens. The plasma will dominate the magnetic field, and since the plasma is moving radially outward, it will carry the magnetic field with it, and basically what does to it, the magnetic field will bend backward, because on one end it's connected to the star that is rotating. On the other end, it's open to the interplanetary medium. Now, what models of the sun and the solar corona and the solar wind have been predicting that we see two regions around the sun. The inner region is what we call the solar corona. The outer region is what we call the solar wind. Within this region, the magnetic field is so strong, and it rotates rigidly with the sun. And this one is the opposite. It's what I described earlier. The only problem with these models is that they predict that the transition between this regime and this one occurs at about 10 solar radii. Meaning that if you are further away from this 10 solar radii, let's say at 30, 40, 50 solar radii, we should see the speed of the solar wind almost radially. the tangential component should be very, very small. And that's actually what is predicted by model. This blue line here is the model, the best model we have for the solar wind. And this is the tangential component of the solar wind as a function of distance. And you see it is very, very small. Now, these are the measurement of that same tangential component as measured by SWEEP, which is the instrument on Parker Solar Probe. And in particular, at 35 solar radii or 40 solar radii, we are seeing more than 20 times what is predicted by models. So even at those distances, the solar wind has a big memory of that tangential rotation that is happening lower down on the sun. And this is really a big, big surprise. We never expected this. And what I'm showing here is from the first orbit, basically. Now when we got closer to the sun, we actually saw another surprising thing. This curve here is the rigid rotation of the sun. But this tangential component, sometimes it gets even above the rigid rotation. So the mystery is even bigger than we thought. There must be something that causing the sun, the solar wind, to keep this memory of rotating with the sun way, way, way out than we expected. And this is a big phenomenon, and it has big implications on many, many other topic of research. One of them, for example, one of the thoughts is maybe the sun, when it was a young star, was rotating way faster than we thought. And if it is true, then the solar model that we have probably needs some tweaking. And if we tweak the solar model, probably we have to tweak other models for other for other stars as well. So this discovery has a big implication on many research domains. Now, a recent paper by Len Fisk and Justin Casper basically what they are saying, that there was a prediction a few years ago by Len Fisk in particular, saying that the open magnetic fields of the sun at the poles gets carried toward the equator by what we call interchange reconnection. You get the closed magnetic fields and the open one, and basically they reconnect to create a new system. And that way the magnetic field lines will travel from the poles to the equator. And every time you have interchange reconnection like this one, you will have a jet of plasma. And it's very fast. And when it propagates outward, it may cause actually some of this tangential rotation with the sun. This is one explanation, but there are other theories as well. And it is by no means that we understand what is going on. We are really scratching the surface here. We are at the beginning, and this probably will take more time. We need the spacecraft to get closer to the sun and give us more measurements to understand what is going on. But as I said, this is a huge discovery by the mission that was completely unexpected. Let me say this. Now I'm moving to the energetic particles. When we launched the mission in 2018, we were at deep solar minimum. When you look at the sun, it remained spotless for almost a year or more, for nearly a year. When you look at it, it's blank. There is nothing going on. And one of the concerns that we had, we talk about internally, is that we have a whole suite that is supposed to measure energetic particles. And if the sun remains quiet for a long time, like the last deep minimum in 2008 to 2010, so basically we have this suite up there, but it will observe only background. It will not observe anything. But we were surprised. Once we got close to the sun, we saw a multitude of small energetic particles, lots of them. And you can see them here. The black curve here is the orbit of the spacecraft. And since the ESAs have two instrument suites, one measures the lower end of the energetic range and the other one the higher end, the epi-low measurements are the inner side of the orbit, the epi-low, epi-high are the outer side of the orbit. And as I said, we see several of these events, although the sun is very quiet. There is another mysterious aspect to them as well. Some events, you see them either in the high energy or at the low energy, but you don't see them at both. And obviously there are others, you see them at both. there is one mystery that we don't know yet, is where this energy, where these small events are, where they are coming from. Because when you look back at the sun, you don't see much going on. Yet in the corona and the solar wind, you see these small events. So the particles are energized somewhere, but we don't know exactly where they are coming from. By the way, there are few events we can link them to some phenomena that are occurring with the sun, but many of them we don't know, and that's a big question. But let me tell you what is the importance of these small events. They have a big importance. We know that whenever you have a big event, they accelerate energetic particles to almost the speed of light. But obviously, these particles do not really start from zero. They have been already energized to some level of energy, to some energetic level. And these events just bring them from that level all the way to the speed of light. These small events that I'm showing here, they play basically that role. What they play, they accelerate this particle to that medium level, energetic level. And once they basically create a seed of particles, energetic particles. And once we have a big flare or a big CME, they will just take this population and energize it all the way to the much higher energies. And by the way, this is one of these events. There was a small explosion here. It's a very small flare, and what it caused, we see type 3 bursts here that is seen by fields, but also we see a lot of energetic particles. By the way, this event here is rich in heavy ions. Although it is very small, it is very rich, and that's actually why we think that these small events are so important to create that seed particles. By the way, this seed particle population has been predicted for a long time, and we believe that Parker Solar Probe is giving us the very first hints how it is created. Now, let me talk a little bit about in terms of publication and science productivity of the mission. We published our first discoveries back in December 2019 in Nature. We had 4 science papers. We had also the editorial. We have News and Fuse. We have News and Focus. We had the cover, which is very beautiful here. But we also got in Nature Astronomy a piece by Gene Parker, after whom we named the mission. After that, we had a special issue in Astrophysical Journal, where we have 55 papers. And obviously, after that, there are many other papers that were published. But right now, we are working on 2 special issues at the same time. One of them will go to Astronomy and Astrophysics, and it will report in new discoveries from the last 2 perihelia, which were closer to the sun. But the other special issue, which is for GRL, you might be surprised by this, but it's only exclusively about Venus. And remember, Parker Solar Probe is not really a Venus mission, but still, every time we fly by Venus, we make measurements there. And what we are discovering is that the measurement by Parker Solar Probe are probably the most sensitive ever measured around Venus. And as a result, we are having many papers written about these 3 flybys, and these will be published very soon in GRL in a special issue. So within a year, we would have several papers in Nature. We would have also 3 special issues, which is, I believe it's a first. No other mission had 3 special issues in a single year. And we expect way more from this mission, by the way. Now, let me conclude with this. Going back to history, it took us 60 years to realize this mission because it's extremely challenging. But once we realized it, as a community, we were emboldened. We actually started thinking about some more challenging concepts and ideas for other missions. One of them is what we call the interstellar probe. And remember, this one is the 3rd concept that were proposed by the Simpson Committee. This concept now, NASA is considering seriously to implement it. And we actually have a study that is conducted at the Applied Physics Lab for the implementation of this mission. And this study were only is basically the result of realizing Parker Solar Probe. There are other concepts also that the community are thinking about, like for example, covering the sun, have 4-pi coverage of the sun. Basically having constellation of spacecrafts that are orbiting the sun in a way that you have coverage from all sides. You will not miss anything. And this is extremely challenging because putting this spacecraft in those orbits is not evident at all. But now we are considering them. Another concept, for example, is having a spacecraft or a number of spacecraft orbiting the solar poles close to the sun, because there is the solar poles is the other mission, the other region that we didn't see, we couldn't observe before. So what Parker Solar Probe is realizing Parker Solar Probe basically is pushing us toward this extreme and challenging ideas that just a few years ago we thought we were thinking that they were not, we will not be able to implement them. But having a mission like Parker Solar Probe is extremely important. And remember, this is the first time that humanity orbits a star. And if you think of it, a star is probably the ultimate object that we can orbit. So by Parker Solar Probe, we are covering basically almost the whole solar system. So thank you very much, and I'll be glad to answer any question if you have any.
Well, thank you. No, that was absolutely fascinating, and your enthusiasm and excitement is infectious. Can I ask members to unmute and show our appreciation? Peter, would you like to call anybody for questions?
We have some questions, and we can probably take a couple more. Neil, I think, Neil, you were first on the list. Would you like to ask your question?
Yes.
There, Neil? I can't see you.
Yes, thank you, Peter. Yeah, I've been looking forward to this talk ever since it was announced, and it was exactly what I hoped for. Fascinating. Thank you.
Thank you. Thank you.
My question, I've got two questions, two-part question. If the instruments are on a lot more than originally anticipated, what additional measures have you had to introduce to manage and process the increased data volumes? And the follow-up is, and has the increased data volumes made discovery easier or more difficult?
Excellent. Both questions are really excellent, and they are point on. Well, let me say this: as scientists, and any scientist, we are always hungry for more data. We never complain to get more data. So obviously, as a project scientist, one of my duties is to make the mission very successful. And one aspect to make the mission very successful is to bring as much data as possible. The thought behind this is this mission is so unique and so historical, and we may not have a mission like it in probably the next 20, 30, 40 years. We have been waiting for it for 60 years. So our duty now is basically to ensure that there are plenty of data that we may not use them now, but future generations may use them. So, so in terms of processing, once we have pipelines that were set on prior to the in the build phase of the mission. So having more data is not really a big deal. We can process all the data we get from the mission. In terms of having the instruments on more time, whether they lead to more discoveries or not. Yeah, that's a very good question, in the sense that limiting the observation to a quarter of an AU, yes, that will allow us to observe what is going on close to the sun, but it doesn't allow us to follow this phenomena as they propagate outward into the interplanetary, toward Earth in particular. So extending the time that the instruments are observing will allow us to follow this phenomena as we move out. And following this phenomena is extremely important, because the solar wind is not only created close to the sun and heated close to the sun. After that, it just flies flies away. And no, there are actually a lot of physics and phenomena that occurs along the way. And we knew that even before Parker Solar Probe, because from one EU observations, we knew that along the journey, the solar wind is being affected by turbulence, by waves, by other phenomena as well. And that's actually one of the fundamental reasons that we could not access to the mechanisms that cause the solar wind in the first place when it is born in lower down in the solar corona. So having more coverage is always good. And let me add to this. Add to the coverage is another side of the coverage as well. Having other missions like Solar Orbiter that launched at the beginning of the year, and another mission that is a mission, Pepe Colombo, having missions like this and working together, basically we have more eyes onto the sun and its environment from different viewpoints. And having this, the more eyes is extremely helpful, because sometimes you need a lot of more measurements, measurements from more than one source to get a handle of certain things. And we are working with Solar Orbit and with Pepe Colombo and with other observatories, both ground and space, and we are actually doing really a fantastic job there, which is I believe that the next decade will be the golden age of solar and heliophysics research.
Thank you for that.
Thank you very much.
Ian Smith was next. Ian, do you want to ask a question?
Hello. You showed an animation of the orbit of the probe around the sun, elliptical orbit, and it looked as though it went reasonably close to planets from time to time. So I'm just wondering how the probe deals with the gravitational perturbations that these close passes would have on its elliptical orbits.
Yes, excellent question. Well, at least for Venus, we need Venus. We need Venus to get closer and closer to the sun. And every time we fly by Venus, we have to do it almost perfectly, because the following orbits will depend on that flyby. And so far, from the first gravity assist by Venus, they went way better than we expected. As for the only other planets that we can fly by is Mercury, but Mercury is very small. It does not really do much to the mission. And I checked the orbit, and we don't really fly by Mercury at all. But what is important for us is Venus. Venus is the most important planet for us. Let me, since I love history, let me go back and also touch on history a little bit. As I said at the beginning of the talk, there were many concepts before to implement a solar probe, and all these concepts basically they were based on sending the spacecraft all the way out to Jupiter, make a gravity assist by Jupiter, and come back to get very close to the sun. And obviously, if you do that, you will have probably one flyby. If you are lucky, you will have two flyby by the sun, and after that, the mission is over. And these missions are costly, and they are also risky. It's the study that were conducted at the Applied Physics Lab in the 2005, 6, and 7 that actually looked at this mission from a different aspect. If we use Venus several times, seven times in the case of Parker Solar Probe, we can get closer to. We will not get much close. We will not get as close as the Jupiter flybys, but we get very close to the sun. But the other advantage of that is that you will have a much longer mission. Instead of 2 flybys by the sun, we will have 7 years, and potentially longer, because the last 3 orbits, the last orbits are stable, and the spacecraft will remain there for forever, potentially. So having a mission that lasts for very long is very advantageous. So we are so lucky to have Venus to use it to have Parker Solar Probe getting close to the sun.
Thank you very much for that. Sean, you had a question.
Yes, I did. Firstly, Dr. Raouafi, I want to say thank you. I think the work you're doing, it must be some of the most inspiring and exciting work in astronomy today. My question really relates to something you touched on earlier, which was how the other missions interlink at the moment. I was curious. You'll be aware recently of the data from the European Space Agency solar probe on campfire mini flares and the possibility they have in coronal heating. And I wonder, when you get data from other missions like that, how does that affect your prioritization of what you want your mission to do? Do you actively decide to maybe change and look at something sooner than you thought you would have, depending on other data you're getting from other missions that you're working with?
Excellent question. First of all, let me congratulate the Solar Orbiter team. They did a fantastic job, and the data they showed us so far, it's amazing. It's like Parker Solar Probe. It's just going to change our view on the sun and its environment as well. And by the way, the two teams, Parker team and Solar Orbiter team, there is a lot of overlap between them. So when the mission are being developed, we knew that we are going to do science together. And that's why the two missions are complementary to each other. There are measurements that are similar between the two missions, but there are also measurements that are completely different, that are specific to each mission. So, and as I said, we are working very, very closely together. There are certain periods of time, the two spacecrafts are aligned together. And those periods of time are extremely important, because what we want to see, we see the same parcel of solar wind measured by one spacecraft and later measured by the other one. This is just one example of how we do science together, because that will give you the evolution with time, but also with space. The other thing also that Solar Orbiter will do that will be extremely helpful when it gets out of the ecliptic, it will first of all give us a view of the solar poles, which is extremely important for other physics of the sun, but also it can help us to constrain the geometry of structure like coronal mass ejections. To see them out of the ecliptic, it will give you the other dimension. And that is extremely helpful. Let me mention the third observatory, which is also a first. It's the DKIST, which is the 4-meter telescope that is built in Hawaii, and it will be operational later this year. It's the 4-meter telescope. It's the largest telescope ever built, and having these three together at the same time is extremely important. One of them will get closest to a star ever. The other one will go out of the ecliptic to measure the solar poles for the first time. And DKIST will measure structure on the sun as wide as a few tens of kilometers.
Wow.
And both these three together, that's actually why I mentioned this decade is probably the golden age of solar and heavy physics research, because having these three together at the same time is unprecedented. And it's just a good coincidence. It was not really planning or anything. It was just a good coincidence.
That's wonderful. Thank you.
Thanks very much.
I'm conscious of time. Are you okay for some more questions?
Absolutely, no problem at all.
Yeah, we've got one more from the members, and then we'll move to YouTube and then see if we can fit any more in after that. So we've got Geraldine and Carl who are going to ask a question.
Thank you very much for your, Dr. Raouafi. Thanks very much for your excellent talk. I was curious about the images that I've seen. Are they visible in a different wavelength does the probe see in a different wavelength, or how does it see things differently to Earth-based astronomy?
The Whisper, which is our only imager on the spacecraft, is basically image the corona and the solar wind in the white light, the visible, and it goes from 450 to 700 nanometers. So it's one band. It's broadband imaging, and it's similar to other coronagraphs that we have. Well, it's better because it's more performant in terms of imaging, but it's in terms of the nature of the images are similar to other coronagraphs in white light we flew in space before.
sorry, I've seen images of particularly of solar flares or the granularity on the surface of the sun, and wondered why that can't be seen with a high resolution telescope from Earth.
Well, we are far away. That's one. The other thing also, we have always atmosphere on the sun around Earth, and that's challenging. We have also weather. So seeing is very important. And as I said earlier, when you get closer to the source, you will always see details. Okay. But you miss when you go far away from the sun. Like this campfires from solar orbiter. We had hints of them before, but once you get closer and closer to the sun, you will see them in much better contrast.
Okay, thank you.
Yeah.
Mark, can we go over to YouTube now, and then we'll see if we can sweep up anything else at the end.
Okay, yes, we have a couple on YouTube. One from Nancy, she's asking, are there real difficulties, challenges communicating with the probe because of the environment in which it's operating, obviously with the solar wind and its orbit as well? It's a pretty roundabout way of getting to the sun, obviously. So what are the challenges involved in communicating in that environment?
Communicating with the spacecraft.
Yes.
Okay, excellent question. Yeah, there are it's challenging to, in particular when you are very close to the sun. It's extremely hard to communicate with the spacecraft. First of all, you don't really want to disturb your spacecraft around the star. You want it just to care about itself and do what it's supposed to do. So when we are close to the sun, by nature, we cannot communicate with it. But also the other thing, also, we want it to be autonomous 100% and just carry on the program that we uploaded to it. There are periods of time when we don't talk to the spacecraft at all. And these are, I would say, well, I wouldn't use the word agonizing, but they are very stressful because you don't know what is going on with your mission until the next time you can talk to it. During encounters in particular, we have one mode of learning just a little bit what the spacecraft is doing. We call them beacon tones. And these beacon tones are a very small amount of telemetry. It tells you the overall state of the spacecraft, whether it is operation mode 3, level 3, which is the best mode, or it demoted to level 2, or even worse to level 1. We've never been to level 1 so far at all. These are the only things, and we get them every 2-3 days. But there are sometimes you don't get them at all, and it's a little bit stressful. After that, once we move away from the sun, we can talk to the spacecraft almost all the time. The only challenge there is to downlink your data. You need geometry. You need your antenna to face Earth, and that is not available all the time. So there are times that we cannot bring data down. We have to store it on the spacecraft and bring it down later. But as I said earlier, the spacecraft is so good, it's so performant, and also thank you to our friends on the DSN on the ground. We are bringing a lot of data, way more than we expected. So yeah.
Very good.
Okay, thank you. We have a question from Deride, I think his name is. I'm not quite sure what he's asking for, but he's asking for your data here. Basically, he says, how can I get hold of the Pocket Solar Probe 1-minute magnetic field and plasma data? He can only see the hourly data, and also he wants thermal and magnetic pressure data as well.
Okay, that's really an excellent question, and we have once we get the data, we have 3 months to calibrate the data, and after that we release it to the public. And we release it in NASA archives, but also from the instrument SOCs, the Science Operation Centers. You can get it from there, or from APL, the Science Gateway of the mission. You can get all sorts of data, all the data you are looking for. And if you don't, I believe I put a slide on it here, but it's probably in the backup. Let me put just my email again. please, if you need the data, email me and they will send you all the details. I'm sharing my screen again that you can get my email. So please email me and they will get you all the data. But what you are asking for, we already have it out there for the first 3 orbits, and soon the orbit 4 data will be released in September 15.
Okay, thank you. Back to you, Peter.
Is that you done, Mark? Well, there was one quick one from Nigel, I think, to round us all off.
Thanks, Peter. Thank you, Dr. Raouafi, for a fantastic presentation. It was very, very enjoyable. It seems to me that the heat shield is a very crucial component in the spacecraft. So I wondered how the heat shield technology was developed, and whether that development for heat protection continues for future missions.
That's really a fantastic question, because there is a story behind it, and I like to tell story. So Parker Solar Probe was at the top option of what we call decadal surveys of NASA from the academies, and obviously NASA tried to implement always the top missions. But even before then, in 2001 in particular, NASA reached out to APL and basically commissioned APL to look into materials that can make a heat shield to protect the spacecraft. And it is obvious there, if you don't have a heat shield, you don't have a mission. And it's only when APL, after I believe 5 years, 6 years, when we knew that we knew what material to use, that NASA, yes, it's decided yes, we are going ahead with the mission. So the research and development of the heat shield started way before the mission itself, 6 years before the mission itself. Yeah, and for the technology itself, there are other missions that will benefit from it, definitely. But for other uses, I learned from our engineering team that certain companies and certain entities reached out to APL to learn about this technology, potentially to use it for other purposes that I'm not aware of. But this is really an invention. It's a brand new invention, and it will have many uses in the future, certainly.
Okay, thank you very much.
Very good. Thank you very much. And back to Andrew.
Thank you. Look, thank you very much again, Dr. Raouafi. The thoughts of water-cooled solar panels whilst we're in the middle of a Scottish summer is an interesting concept. But please, can you thank Justina and all the team?
Absolutely.
Our best wishes for the rest of the mission. Thank you very much indeed.
Thank you very much. I appreciate it.
Thank you. Can we show our appreciation? Thank you very much.
Thank you.
Okay. Right, Mark. I don't know if anybody else has got any more discussion we want to have, but we can let Dr. Raouafi get back to work if he wants.
Can
He's
I
still
just
got the rest of the afternoon.
Can I just say, Andrew, our latest member, Emma, is on for the first time tonight. Because can we welcome Emma Burrell?
Emma Burrell, yes. Emma, can we all welcome Emma? Despite the lockdown, our membership continues to grow. So we must be getting something right. And I think the quality of these talks has been a key factor in it. Thank you very much. And with that, I'll say good night. Thank you.
Thank you.